Yeah, sure. But again, that doesn't matter, right? All that matters is that the acceptor is electronegative. What did I say was the most important thing, or one of the most important things in all of biochemistry? Shape. Look at these shapes. Look at the shapes of the hydrogen bonds. They're all straight. Hydrogen bonds must be straight, right? If you veer too far off from a 180-degree bond angle, the strength begins to go down precipitously. So the strongest hydrogen bond that we can have is one where the bond angle is 180 degrees, down to about 175 to 180 degrees, and vice versa, right? But hydrogen bonds must be straight. We cannot have a hydrogen bond where the hydrogen bond donor is this and the hydrogen bond acceptor is down here, right? We need all three atoms to be in a line. Angles are no good for hydrogen bonds. Hydrogen bonds, again, are demonstrated in base pairing. They're going to be demonstrated in many, many different interactions that we see between those macromolecules and metabolites as we go on through the semester. Now, van der Waals interaction. Van der Waals interaction is another head scratcher, but I think this illustrates it very well. Van der Waals interactions are the weakest of the non-covalent interactions, right? They are the weakest. And they're so weak, in fact, that we can really only observe them between uncharged molecules, right? In other words, probably nonpolar or hydrophobic molecules. The reason is that they're so weak that if we have an ionic interaction, that's orders of magnitude stronger, so it just overwhelms anything that we would measure with van der Waals. The same is true for hydrogen bonds. They're much stronger than van der Waals. Van der Waals are very weak, but they are important in what we're going to see in a minute, right? So what is a van der Waals interaction? Well, let's say that we have two uncharged things, right? Two uncharged molecules, two uncharged atoms. There's no ionic interaction, obviously, between them because the electronic charge on both of them is zero. Let's say that we don't have any hydrogen bond donors or acceptors, so these shouldn't interact at all. But what's observed is that they tend to actually, well, I don't know why that's so weird, they do tend to actually interact. So how are they interacting is via this van der Waals force, because though we tend to think of the electron distribution, right, or the charge distribution around these non-charged atoms should be perfectly spherical at all times, that actually ends up not being the case. If we look at time one, sure, let's say that at time one we have this perfectly spherical charge distribution around the atoms, but at time two, well, this green atom will momentarily lose that perfectly symmetrical spherical distribution of charge, such that this side is going to be slightly more negatively charged, and this is going to be slightly more positively charged. Because again, if one side becomes more negative, the other side has to become more positive because the overall charge isn't changing, right? So this is very slight. But what happens is that when this side becomes positively charged, that induces a complementary charge here. This positive charge will attract ever so slightly some electron density away from here so that we end up with a partial negative on this side, and then of course a corresponding partial positive on the other side of the atom. And now we have, again, momentarily and very weakly, we have attraction here, right? Where is this attraction the greatest? Is at the van der Waals contact radii, the van der Waals contact distance. What this means, well, if we look at this charge here, if we look at the energy between two hypothetical atoms as they come through, like in our example before, okay, they have the lowest energy when they are a certain distance away from each other. That is the van der Waals contact radii. And when you look at molecules or whatever in their space-fill view, right, so that each atom is a sphere, the radius of that sphere that's being detected in the space-filling model is the van der Waals contact radii of that atom, right? And why is that? Because it kind of gives our monkey brains an idea of, well, this is how big, quote unquote, the atom is. Why? Well, if we try to push anything into that atom beyond the van der Waals contact radii, close that distance, Well, now our energy begins to shoot up humongously, right? So we can't push anything into that atom really beyond that van der Waals contact radii. So really, an atom is as big as its van der Waals contact distance, right? Which is why we show it as kind of a ball of that size. That's not actually the case. Obviously, an atom isn't this, steel sphere that's very small, but it gives a good approximation for how big, right, or how close you can get to that atom before the energy required to do so has to be way too big. Conversely, if we have two atoms that are close together at their van der Waals contact radii, well, because that's the most stable, the lowest energy, right? Well, now we try to take them apart, right? Well, now that's going to require some energy as well, okay? So they're most stable when they're at their van der Waals contact radii, and this explains something in DNA called base stacking, right? So here we have one base pair going this way, another base pair down here, another base pair here. So our DNA is going up and down, and we're looking at the base pairs horizontally. If you notice, each of these base pairs are stacked on top of the one below it and the one above. Let's just look at the one below, right? They're stacked parallel, right? So this is base stacking. This is mediated by van der Waals interaction, right? So if we're at our van der Waals contact distance, and one base pair tries to tilt, well, now these are too close together and are going to be repelled. And where did the energy come from to take these two apart, right? It doesn't come from anywhere. So that van der Waals interaction helps to maintain those base pairs stacked parallel on top of each other. So we see that all of these, so far, all of these different interactions play a part in establishing the structure of macromolecules. In this example, DNA, we're going to go over how this works for proteins on Thursday. But here, for example, the covalent interactions hold the sugar phosphate backbone together and stabilize the bases, the nitrogenous bases. By resonance, the ionic interactions have to be overcome in order to stop those phosphates from repelling the other strand. Hydrogen bonds help to bring the two bases together. Van der Waals interactions help to stabilize the overall structure of DNA by enforcing base stacking. And then lastly, we have here the hydrophobic effect. Hydrophobic effect isn't really a force, but instead it's an illusion. And it has to do with entropy, right? If we look at entropy, or if we look at a system of water, well, water is very interesting in that it's so small, but it's an electric dipole. It means that it can form hydrogen bonds in itself. We have two sites for hydrogen bond acceptor here. On this oxygen can accept two hydrogen bonds, but notice we have two hydrogen bond donors as well. So each water molecule can participate in as many as 4 different hydrogen bonds, usually with itself. The extent here, right, really just determines what phase the water's in, right? So if we're exhibiting all 4 hydrogen bonds, that's ice, right? We have 3 hydrogen bonds, or 2-ish, well, now we're water. If we have very few hydrogen bonds, now we're steam, right? So the number of hydrogen bonds corresponds to the phase that we're in. But what is important is that when we have this configuration, this is the lowest energy configuration. It's forming hydrogen bonds in water. These hydrogen bonds are constantly being made and broken, but the total number of hydrogen bonds that are formed is more or less constant. And this is what leads to the hydrophobic effect. So let's say that we have a drop of oil or some nonpolar molecule here. Well, this nonpolar molecule or drop of oil, by its nature, cannot form hydrogen bonds because it's nonpolar. It doesn't have any hydrogen bond donors or acceptors. So instead what happens is that we have to form kind of a cage around this nonpolar molecule. So these waters are not as free to go around and hang out with their other water buddies forming hydrogen bonds. They have to form this kind of cage around this nonpolar molecule. Of course, this is cross-sectional, so that would be happening around the entire molecule. The same is true for this other molecule down here. Now, anyone that's ever, taken or tried to cook spaghetti and put a couple of drops of olive oil in the pot, eventually, right, what happens? Those drops of oil seem to come together. They seem to be attracted somehow. This is actually not the case, right? There is no attractive force between these two, right? go back to our drop of oil analogy, well, they're way too far for van der Waals interaction to do anything. They're not charged, they're not coming together, right? So what is causing these two drops of oil to come together? Well, it's thermodynamics, entropy, right? By combining these two together, right? In the case of oil, making one bigger oil droplet, but in the case of molecules, just having the two nonpolar molecules interact, what we do is we reduce the surface area of these two molecules, right? Here we had this surface area plus this surface area, but by combining them, well, now we remove this face, which was previously in contact with the water. So this frees up the water molecules that used to be here and here to be out now, forming hydrogen bonds with the rest of the water, which is a more stable, lower energy configuration for this system. Because when the bonds are made, when these extra hydrogen bonds are made, energy is released, right? So we're at a lower energy state. This is the most stable configuration of this system. So if left alone for long enough, this will always occur, right? And why does this matter for DNA? Well, remember, the bases are mildly hydrophobic. So while, yes, the hydrogen bonds between the bases are helping to hold them there, the hydrophobic effect, in this case, keeping the water away from those partially nonpolar bases, helps to stabilize the overall structure of DNA. So there's yet a fifth force stabilizing the structure of DNA. This hydrophobic effect is critical for proper structural formation of proteins, like we'll see on Thursday, right? So it's not as important. I mean, it is still important for DNA, but it is even more important once we start to talk about proteins. So I want to get into thermodynamics for a bit. Okay, what's happening? So basic thermodynamics and acids and bases. I don't want to spend too much time on the derivation of this equation here, delta G equals delta H minus T delta S. Here's the derivation that goes step by step. It's also in the book. I don't want to spend a ton of time on this. What is important is to examine this final reaction down here, right? I mean, this is all just algebra starting from up here, right? Saying that the entropy, the delta S, is inversely equal to the temperature and negatively correlated to the enthalpy, the heat of the system. And then from there, we just make several assumptions that eventually get us to this over here, that the delta T times total entropy equals delta H of the system minus T delta S entropy of the system. This term here, right, we just call that Gibbs free energy, right? So that's the most important thing we need to take away from this slide is Gibbs free energy. What Gibbs free energy tells us is if a process will proceed spontaneously, right? So if a process proceeds spontaneously, what does that mean? What does it mean if a process proceeds spontaneously? Right. Instead, it just will happen, right? If the delta G of a process, doesn't have to be a reaction, but the delta G of a process is less than 0, then its exergon means that it will happen spontaneously. It doesn't tell us anything about the speed or the rate at which that process will happen. All it tells us is that that process will happen. Right? And if we look at here, this illustrates something interesting, right? So what do we need in order for delta G to be less than 0? Well, we need this term here, T delta S, to be greater than delta H, right? So let's think about this, just empirically, right? Let's say, well, us, right? Us. We are complex, yes? More or less. Our bodies, I mean, not our minds. Our bodies are complex, right? So it requires a high degree of organization, right? We could disassemble all of our atoms into, put the phosphorus over there and the hydrogen over there and the carbon over there, right? That would be not as ordered, yes? So how did we come together then to put the atoms together in exactly the right way, in a very ordered, specific manner, in order to make a functioning person? Okay? Did the entropy increase or decrease? The entropy decreased, right? Because now we're more ordered. But if we look over here, right, if the entropy decreased, Well, what does that mean? What does that mean in terms of Gibbs free energy? The entropy decreased, so the delta S will be negative, right? So G should be positive, yet we're all here. So how did that happen? Huh?
Through action of enzymes.
Through the action of enzymes, I suppose, but how did those enzymes come to be? Because those enzymes are ordered, it would be easy to separate all the nitrogen and the carbon from those enzymes and have them separate, but instead we put them together into an enzyme. How thermodynamically do we exist if we are more ordered, so that we decrease the entropy, right, of these atoms? What have we done? Sure, but not that high, right? I mean, we're only 37 degrees above zero, so it's not crazy. We're not talking about thousands of degrees. If this is positive, or if this is negative, right? Delta S is negative. Minus negative means that this will be positive. Which means, let's say that delta H is 0, right? Which means that then delta G will be positive. But we're here. So delta G then must be negative, right? If delta S must be negative, just by the nature of us existing, and delta G must be negative because we're here, then what does delta H have to be? Very negative, right? Very negative. And in fact, that's the case. What are we giving off all the time? Heat, right? And where does that heat go? Into the universe, right? And what happens when we heat up the universe? We increase the entropy of the universe. So we are locally decreasing entropy by existing, while at the same time increasing the entropy of the universe, right? In order for any process to take place, delta G must be 0, which means that the entropy of the universe is increasing always and forever, right? So by us existing, you are directly contributing to the heat death of the universe. Now, how does this apply to DNA? Well, let's consider that we have, all these single strands of DNA, right? And what we observe is that we mix these together, and let's say that they're complementary strands, so that the bases do work together. What we observe is that they spontaneously form a double helix. Now, this is kind of interesting because here we have way more entropy, yes? We have 8 more molecules, and these single strands of DNA are much, wigglier, so they can adopt more configuration. So there's way more entropy, way more randomness here than here, which means that delta S, what is it, positive or negative? Going from here to here. Entropy is decreasing, so the change in entropy is then
increasing.
Negative, right? But again, we have minus a negative. T is always going to be positive, obviously. Well, I say obviously because T is in Kelvin, so we can't have that, right? So T is always going to be positive. Delta S, in this case, is negative. Minus a negative is plus, which means that delta H then must be at least as negative as this by magnitude, right? So if delta H is negative, what does that mean? Well, same for us, right? Heat is being released. And in fact, we can measure that. And it is measurable that when DNA strands anneal, which is the same base pair, heat is released. We can measure that in a Von calorimeter. And it is true. So this always holds true, right? The entropy in the universe increases even if the local entropy decreases. And the way that that's dealt with is by releasing heat, right? If a process yields a lower entropy state, then heat must be somehow released from that system. All right, now on to acids and bases for 20 minutes, which is fine. So, we are going to be dealing with some acids and bases in this class, which I know is everybody's favorite. And I don't really care about pH, right? But what is important to understand about acids and bases are weak bases and ionizable protons, right? Which each have their own, what we call a pKa. So let's just very quickly go over just pH and pOH, right? Don't spend too much time on this. But essentially, pH is what? Well, first, what is the P in the pH? What does that mean to you?
Negative log.
Yeah, pH is a mathematical function that means negative log, right? The negative log of Dr. Villegas is P Dr. Villegas. That's all that means. So pH is simply the negative log of the H plus concentration. And we know that ranges from, or on a scale up to 14. And how do we know that? Well, if we consider just water here, water ionizes to some degree to get H plus and OH minus. And what we can observe, right, we can actually measure this, is that this equilibrium constant, right, K, is H plus times OH minus over H2O. And this is measured to be 1.8 times 10 to the minus 16. That's just what it is, right? So the concentration of water in water then is 55.5 molar, right? You can try this yourself. There's nothing magical here. You assume that the density of water is 1 gram per mil. Well, what this means then is that H plus times OH minus equals 55.5 molar times 1.8 times 10 to the minus 16, which is this. This equals 1.0 times 10 to the 14. Now, if you notice, these two must be the same, because if H2O dissociates by X, then the amount of H plus goes up by X, and the amount of OH goes up by X. So these must be the same, right? So we take the square root of this, and we find is that either H plus or OH equal 1 times 10 to the minus 7. In other words, pH plus pOH equals 14, always, right? And to find, again, the pH of a solution is simply the negative log of the H plus concentration. Now, what if, so this is all well and good. Let's see if I have, oops, sorry. Yeah. All right, fine. So what if we have then a strong acid? Well, this is easy, right? So we have, for example, HCl. So let's say that we have then HCl. I'm going to take this out. All right, tell you the chalkboard situation.
I forgot that you were
Oh. So we have HCl, a strong acid. This dissociates completely into H plus and Cl minus, right? So let's say that we added 0.1 molar of HCl, right, initially, and we had 0 and 0. Well, what's going to happen? Well, the change, right, our ice table, this will go down by 0.1 molar, or near enough to not matter. 0.1 molar. This then will go up by that same amount, plus 0.1, plus 0.1 here. So at equilibrium, we have effectively 0 HCl. We have 0.1 molar H plus and 0.1 molar Cl minus. So in our case, the pH is negative log of 0.1, which notice is the same as the amount that we started with. So for a strong acid, the pH of the solution is just negative log of however much concentration of acid you added. Easy enough. But what if we have an acid that doesn't completely dissociate? Like, for example, acetic acid. Well, acetic acid, if I go to here, CH3, So here we have acetic acid. I'm going to write this as HA. H for the proton, and A for just whatever's left over, the conjugate base, yes? This proton here is the ionizable proton. It is the acidic proton, but it is very bad at leaving, right? So if we add acetic acid to solution, it's not going to do like hydrochloric acid did and completely dissociate into H plus and A minus, in our case, H plus and acetate. Instead, it's only going to dissociate by a certain amount, right? And that amount is determined by the pKa of this proton. So let's see what we mean by that, by all that, right? So let's say that we have, again, our acetic acid, HA. This is going to dissociate into, again, H plus and A minus, right? So let's say that we add 0.1 molar HA, and we start with 0 of both of these, right? The amount of H plus in the water, 1 times 10 to the minus 7 molar is negligible, so we're not going to deal with it, right? So that's where we start initially. This HA is going to ionize by some amount. I don't know, right? X. That means that H plus will also go up by that amount, and A minus will go up by that amount. That means that at equilibrium, what do we have? Well, we have whatever we started with, 0.1 molar X of HA, 0.1 molar of HA minus X. We don't know what X is, but that's what it is, right? And that means that also at equilibrium, H plus is just X, and A minus is X. So our equilibrium constant K is X times X, so X squared, over 0.1 minus X, right? What is this K? So this K, we call it special. We call it the acid dissociation constant, Ka, right? Whatever this is, it is, right? This has been measured experimentally for basically any weak acid, right? This kind of acid that doesn't totally dissociate, we call that a weak acid. In the case of, for example, acetic acid is 1.778 times 10 to the minus 5, if I remember right. .778 times 10 to the minus 5, yes. Right? So there we go. So now, well, we know that Ka, we know what we started with. What do we have now? We only have one variable. This is now easy to solve. This is a quadratic, but it can be solved. Once we have X, well, X is just equal to the H plus concentration, right? So to find the pH at equilibrium, well now, the pH of a 0.1 molar solution of HA, of acetic acid, at equilibrium, is simply negative log of whatever X comes out to be, right? Very good. So, now that we know about the acid dissociation constant, again, write down our HA yields H plus A minus, Ka equals H plus and A minus over HA, right? We're going to derive a very useful formula that's going to illustrate something important relating back to this thing that I told you about, pKa, and what that actually means. And that's going to be important as we start to talk about different reaction mechanisms that are going to involve dissociable protons. All right, so here, let's rearrange this to see that Ka equals H plus times A minus over HA, right? This is the same, nothing has changed, nothing magical has happened here. Let's take the log of both sides. Log Ka equals log of H plus. Now, because of our log rules, right, if this is all in a log, well, log of H plus times A minus over HA is really just log of H plus plus log of A minus over HA. Yes? All right, this is just normal math. Okay, so let's subtract. What do we want to do? All right, let's multiply everything by -1. Right, so what does that give us? Well, this gives us negative log Ka equals negative log H plus minus log A minus over HA. Correct. pH equals I see. So we get pKa equals pH minus log A minus over HA, right? Because here we have negative log of Ka, so we'll just call that pKa. We have negative log of A plus, so that's our pH, minus log of A minus over HA. And let's move this term over here. So what do we end up with? pH equals pKa plus log A minus over HA. Right? Here we have the Henderson-Hasselbalch equation. And this is the first time that we're actually seeing pKa. So what does pKa mean? Right? Well, let's consider what happens if the pH of a solution is equal to the pKa of a dissociable proton. For example, here in this acetic acid example, right, the pKa of this proton is 4.75. Okay, that was just determined experimentally. That's just in the nature of this proton. Well, if pH equals pKa, so let's say that 4.75 equals pH 4.7, or pKa rather, 4.75 plus log A minus over HA. Well, now let's subtract from both sides. So this is 0 equals log A minus over HA. So what must A minus over HA be? The log of what is 0? Log of 1 is 0. So that means that A minus over HA must be 1. What does that mean about A minus and HA? They're the same. When the pH of a solution matches the pKa of the proton, that means that that exists as 50% A and 50% HA. So that proton is 50% gone at when the pH equals the pKa. Now what happens if the pH is lower?
They're inversely related.
Huh?
They're inversely related. So pH is low.
No, the pK never changes. The pKa is in the nature of that proton. We cannot affect, well, we can. We'll get to that later. Sorry, getting ahead of myself. But let's say for now, we cannot change the pKa. There are other ways that we can that has nothing to do with pH. If the pH decreases now, right, say that we're at 4.75, so we're at 50% here and 50% here, right? If we decrease the pH, is the ratio of this going to change? Which one do you think is going to get bigger? Why? Huh? That is more acidic, but if we decrease the pH, we're adding more protons, right? Which means we can make more HA. Let's see if that's the case. So let's say that we decrease the pH to 4. So pH, oh yeah, let's just rearrange this to make our lives easier. pH equals pKa, so A minus over HA equals 10 up to the pH minus pKa, negative pH minus pKa. Is that right? Alright, there we go. A minus over HA equals 10 up to the pH minus pKa, yes. Okay, so let's say that we decrease the pH to 4. The pKa is still 4.75. So our A minus over HA is what? 4 minus 4.75. 0.177. So which is bigger, A minus or HA? Right. If A was bigger, then it would be greater than 1. Right? But in this case, it's less than 1, so that means HA must be bigger. So indeed, lowering the pH increases the amount of HA. Conversely, increasing the pH increases the amount of A minus. So what we say then, why pKa is important, right, as a value, as a unit, is that we can look at any proton, right, in any environment and see what is the pKa of this proton. And we can say, all right, well, if the pH is lower, that proton is there. And if the pKa is higher than or the pH is higher than the pKa, then that proton is gone, right? So it gives us a good baseline to see what state is our weak acid or dissociable proton in, right? If, again, the pH is lower than the pKa, it's protonated. If the pH is higher than the pKa, then it's deprotonated, right? You get more practice on this in your homework, I promise. All right. All right, that's all I really care about covering. So we're going to stop here for today. I'm sure everyone's brains are doing just fine.